All right. Okay. So today, it's Friday, and man, I feel like if it weren't for these classes where I'm putting in the day of the week, I feel like I would lose track of time here. Um, but uh, but here we are. We're talking regularization. Okay. And so, what is regularization? Oh, what happened to my? All right. So it's a method that we use to kind of address the problem of overfitting. Okay. And so, overfitting is the idea that we end up modeling odd specifics of our data. Okay, means we can predict our training data very well, but we can't predict new data. Okay, and we saw this when a couple lectures ago we fit that 17th order polynomial. Okay, when we tried fitting the 17th order polynomial, it fit the training data really well, right? There was very little error on some of those training data points. But then when you gave it new data, because it was so like wiggly, it did a bad job of predicting the new data. So we say, wait, the 17th order polynomial, that's not a good thing. So that's what cross-validation does, right? It says we look at how it fits the training data, but we measure its performance on how well it fits data that wasn't used in the training process. Okay. Regularization is another method. And what it does is it penalizes complex models, okay? It modifies the actual loss function that we're using to penalize complex models. Okay, so what do we mean by modifying the loss function? So far, what we've been using is we've been using the least squares loss function, okay? Which means the way we measure how well a model is performing is we say, well, what's the difference between the actual values t and what our model predicts? Our model predicts x times w. Our actual values are t, and we say, well, what's the difference between t and xw? And we square those, okay? And we add those up, right? And so, in terms of matrix things, we have t minus xw transpose t minus xw. And we're going to say the model that's best is the model that minimizes this least squares or the mean squared error. All right. But the problem with using this and only this is that we might end up picking an overly complex model because in general, as you make your model more complicated, your mean squared error is going to go down, right? So if we're using only the training data, the 17th order polynomial will have a lower mean squared error than the third order polynomial. So we would say, oh, the 17th order polynomial is better because the mean squared error is lower, right? And we go, okay, well, that's obviously not the case, all right? And so what we're going to do here is we are going to say, you know what, the best model is going to have to balance the OLS term, okay, the least squares error, or the squared error term, which is L, plus a complexity factor, okay? So we include a penalty term for the model's complexity, right? And so we're going to call this the regularized loss. This is L prime. The regularized loss is the OLS loss, the least squares loss, okay, which is this, plus lambda times a complexity factor. And so the complexity factor is, is how we measure how complex a model is. And so a more complicated model is going to have a higher complexity term, and a simpler model will have a small complexity term. And basically, we want low OLS and low complexity, okay? And lambda is how the weight of how much the complexity is penalized, right? So big lambdas will multiply the complexity by a lot, and so bigger changes in complexity will increase this a lot more. Smaller lambdas say that complexity is not as important, right? So an analogy to real life is maybe one day you have to consider you have to search for apartments and stuff, and this is a silly, I made up these numbers, so don't, right? Okay, anyway, so let's say there's one apartment you're considering. It costs $2,000 a month, and the commute to work is 10 minutes each way, right? So it takes you 10 minutes to get to work, 10 minutes to get back. You spend 20 minutes a day commuting. The other apartment, it costs $1,700 a month, okay? So it's $300 less a month, but the commute is 40 minutes each way, all right? So you're gonna spend 40 minutes there, 40 minutes back, hour and 20 minutes commuting. So you're gonna spend an extra hour commuting a day, right? If money is the only thing, right? If money is the most important thing here, then making your decisions easy. All you have to do is you pick the apartment with the lowest cost and you say, well, this is the one I'm gonna pick, right? But most people value their time, and the apartment with lower rent comes with a penalty, meaning you have to spend additional time on the commute. And so if you value your time greatly and you've got an active social life or whatever outside of work, or you hate commuting or whatever, then you'd give the penalty of the longer commute, you'd weigh that penalty a lot heavier. On the other hand, if you don't mind the commute, okay, or you don't do a whole lot with your time outside of work, then the penalty for having a longer commute is reduced. You know, you don't love having a longer commute, but you also don't mind it, okay? And so you would, in that case, you'd pick the apartment with the lower rent and longer commute, right? And so what we have is the true cost of the apartment is the rent plus some preference factor times the commute penalty, okay? And that's how we would measure how, you know, the true cost of the apartment. And so similarly, when we are talking about regularized loss, it's going to be the ordinary least squares loss plus some factor, preference factor, times the complexity. And that's going to give us the regularized loss. Okay. Similar structure there. Right? Keep in mind, what we're doing is we are optimizing a loss function. Okay, so this thing looks a little bit like AIC or BIC, but it's different, right? AIC and BIC are values, are metrics that you use after the fact, okay? And if you don't remember what 101, if you haven't taken 101A and you don't know AIC, BIC, that's okay. But those are metrics that you use after the fact to kind of compare models. Here, these are not after the fact. These are actually used in the process of optimizing, okay? So we are going to pick our coefficients. We're going to pick the values of W in such a way that it minimizes this modified loss function. Okay, we're not going to pick the W's that just minimize the ordinary least squares loss, the OLS loss. We're going to pick our W's in a way that optimizes this version of the loss function. That's what we're going to try to do. Okay, and so here it is. Here's a Wikipedia article, and what it comes down to is how do we measure complexity? How do we measure complexity? And how we measure complexity is going to be given by this, I guess, is given by the function R times F, okay? But how do we measure complexity? All right, let me just pause here. Give me a green check if you're following along and if this all makes sense, the idea of picking our W's to minimize a modified version of the loss, okay? We're picking our coefficients W to minimize this modified version of the loss. And if you got questions or something doesn't quite make sense, please let me know. All right. Okay, well, thank you for those of you who gave me feedback, okay? One way we can measure a model's complexity is to count how many coefficients are not zero, okay? And so, for example, we have two models. Let's say we got one model fits a fourth order polynomial and one model fits a fifth order polynomial, right? And so we can say the fifth order polynomial is more complex, okay? It's got, as far as its coefficients go, it's got W0, it's W1 xn, W2 xn squared, W3 xn cubed, W4 xn to the fourth, W5 xn to the fifth. So it's got actually, it's got 6 W terms, okay? However, if you force this last coefficient, this W5 equal to 0, then you get a fourth order polynomial, okay? So just by saying this coefficient has to be 0, we've simplified the model, okay? And so we can say, you know, one way to measure a model's complexity is to say, well, how many coefficients are not 0, okay? And and that will basically tell you how many X variables you are using to make a prediction. And so that's how we can measure model complexity, right? And so how many terms are not zero is known as the L0 norm, okay? So if you have a vector and you take the L0 norm of the vector, it's basically going to be how many terms are not zero, okay? And but here's a problem, right? So if we use this, if we use the L0 norm as our measure of complexity, this is what our loss function would look like. It's the ordinary least squares loss function plus lambda times the number of parameters that aren't zero, okay? If we use this, this turns out to be very, very difficult to optimize, okay? We would say that this loss function is not convex, which is, you don't have to worry about it right now, but basically it just means it's going to be hard to optimize. What you have to do is you have to consider all possible permutations of the elements in W that are non-zero. And when they're non-zero, you have to consider what value W should be. And if you've got more than a couple terms in your model, trying to optimize this becomes staggeringly difficult, okay? And it even gets its own little spot in the Wikipedia article that says how hard it is. So we don't really use the L0 norm, okay? So instead of the L0 norm, we use the L1 norm, okay? So I don't know if you guys remember your linear algebra stuff on norms, and you've got the, L1 norm. Sometimes we call that the Manhattan norm. I don't know if you guys remember that. Okay, L1 norm, and then you got the L2 norm, which is your Euclidean distance thing, okay? Okay, so one way is we can say, instead of counting how many elements are non-zero, we can sum the absolute values of the elements in W, okay? So we'll take the L1 norm of W. So we take the absolute values of each element in W and we're going to add those up. Okay, we're going to say this is the measure of complexity, right? So if W is not zero, it's going to contribute to the penalty factor. Larger values will contribute more to the penalty factor. And then if W is zero, then that variable's not counted, does not contribute to the penalty factor, okay? And so when we try to optimize the loss function, what we have to do is we have to consider, the change in the mean squared error, but also the change in the size of W, right? And a bigger W means our model is more complex, okay? And when we do this, we call this the LASSO. The LASSO is regularized least squares with an L1 norm. Okay. Another option is to use the L2 norm. The L2 norm squared is the squared value penalty, okay? And basically you're going to take the values in W, you're going to square them and add them up, okay? And what that means is that larger values of W are heavily penalized, right? So if W, one of your coefficients is 10 and you square it, then it contributes 100 to this penalty factor. Whereas a smaller value of W, like 1, when you square that, it only contributes 1 to the penalty factor. And values less than 1, like 0.5, when you square that, contributes only 0.25 to the penalty factor, okay? So this is known as ridge regression when you use the L2 norm, okay? And one effect of ridge regression is that it's going to prefer when the W's are similar in size to each other, okay? It's going to prefer when the W's are similar in size. All right, and so an objection that students sometimes have is that they ask, how does the size of a coefficient measure model complexity, right? So the idea of, how many variables are included in the model, that makes sense. That makes sense for measure complexity, right? When you say, okay, well, this model has 4 variables in it, this model has 2 variables in it. Okay, obviously the model with only 2 variables is simpler than the model with 4 variables, okay? And, to say, okay, well, here we have 4 non-zero coefficients and here we only have 2 non-zero coefficients. That makes sense. But now we're using the L1 and the L2 norms, and what we're saying is that the size of the coefficient itself measures complexity. sometimes students have trouble with this, right? So, um, so if you have two models and they have the same number of variables, this model has 4 variables and this model has 4 variables, aren't they equally complex? Okay. Um, just because this model has bigger coefficients, how is that more complicated than the other, right? And especially if you think of units, right? If you just change the units, right? If you go from meters down to centimeters or centimeters up to meters, that's going to change the size of your coefficients. And so if I change my units, then my coefficients would change and that would change my model complexity. That doesn't make sense, right? So those are totally valid objections, and I'm going to try to address these. Okay, I'm going to try to address these things and say that, you know, we're using the coefficients. The size of the coefficients is still a good measure of model complexity, right? Okay, so absolutely, this idea of changing your units affecting model complexity, we want to avoid that. Okay, and so so we almost always recommend that you center and standardize your x variables before fitting the model, right? So centering means adding or subtracting a constant so that the mean of the column is 0. And then standardizing means you multiply by some kind of constant so that the standard deviation is 1, okay? Or that everything has the same standard deviation, right? And then an alternative method is to scale the variables. So all the variables go from 0 to 1 or something like that. That's useful if you have a function that can't accept negative values and stuff. So like a square root or something in there. So so these are ways to kind of address this thing. Okay, wait. Okay, Farah says, for slide 11, could you explain what you mean by reduction in MSE must be greater than? Okay, all right. Let me finish this and I'll go back to that. All right. So standardize means multiplying a column. Okay. Yes, and so this will, by centering and standardizing your thing, then using different units will not affect the size of the coefficients, okay? So, because if you have meters and you have centimeters, after you center and standardize, they're basically on the same scale there, okay? So you don't have to worry about that, okay? Okay, let me take a moment and go back a couple slides. All right, so what we say, when I say this, when we try to optimize the loss function, reduction in MSE must be greater than lambda times the size of W for the variable in consideration, right? So what we're saying is that when, let's say when you're picking your best W's, okay, let's say you can reduce your OLS loss, okay, your ordinary least squares loss, by increasing the slope by a little bit, okay? However, increasing the slope means this term is going to get bigger, okay? And let's say increasing the slope only reduces your lambda by just a tiny, tiny, tiny bit, okay? In that case, you're better off not increasing the slope, because increasing the slope will make this thing bigger, and it only reduces the L a tiny bit. So in order for you to justify increasing the slope, the drop in the L has to be big enough to kind of balance out, or has to be greater than how much you increase W by. Does that help? So so in OLS, you want to pick your best slope and intercept, or whatever terms you all have, but bumping up your slope or your intercept or whatever is going to increase this, which is going to increase your complexity factor, which will make this L prime bigger. But it's justified if bumping this up reduces the OLS term. So if it justifies the OLS term, then go ahead and increase your slope, but otherwise don't, okay? Okay, so let's go back to here, right? So we're going to center and standardize all of our variables, so we don't have to worry about this units thing affecting our model complexity. All right, but then you can still ask, well, how does the size of the coefficient measure model complexity, right? And so here's an example. Let's say there's 2 models, both of them use 4 variables. And both of these models are pretty much exactly the same, except for the coefficient of the 4th variable, right? So they both have 4 variables, Both models have the same coefficient for variables x1, x2, and x3. And the only difference is that model A has a big coefficient for x4. Let's say W4 is equal to 1. Model B has a small coefficient for x4. Let's say W4 is equal to 0.01 for model B, okay? So the only difference between model A and model B is this W4 coefficient. And I would argue that model B is less complex than model A because it has a smaller coefficient for the x4 term, okay? Just this reason alone, W4 being 1 versus W4 equal to 0.01, I would say is enough to say that model B is simpler or less complicated than model A, okay? Because when you have a tiny coefficient, when you have a small coefficient, it means that predictor variable has less impact on the outcome variable, right? So if model B has a tiny coefficient for x4, then it's basically putting less importance on the variable x4, right? Remember, we've standardized and scaled everything, so everything is on the same scale. And basically we're saying that x4 is less important in model B than it is in model A, right? So even though model A and model B both include variable x4, model B is a lot closer to just ignoring x4 altogether, okay? And because it's closer to ignoring x4 altogether, I say it's the simpler model. All right, so here's an analogy, right? Imagine you have two students, okay, and they're both involved in several clubs on campus, right? I don't know, let's say they're both involved in like maybe 4 different clubs, okay? One of the students is fully invested in all 4 clubs, has a busy schedule, and we would say their life is complicated, has a complex life, right? Busy life, fully invested in all 4 of their clubs that they're in, right? The other student, you know, might be involved, but only marginally so, okay, right? So maybe also involved in 4 clubs, but is only marginally invested in each club, right? This student skips a club meeting whenever they feel like it, doesn't sign up for any extra responsibilities, doesn't do any kind of extra stuff, right? I would say, even though this student is still involved in 4 different clubs, I would say this student has the simpler life, okay? Is less complex. Now, whether that's a good thing or bad thing, you know, that's something else, right? I was always taught, if you're going to do something, do it well. But you know, between the one who's fully involved in all 4 versus the one who's only marginally involved in 4 clubs, we would say the one who's marginally involved has a simpler life, okay? And so similarly, we're going to say that if you place a lower weight on a predictor variable, then it means you know, that model is going to be less complicated, right? And so we can say that the size of that coefficient, you know, can be used as a measure for how complicated the model is, right? It can be used as a measure for model complexity. Does that feel okay? All right, okay. So let me just show you the effect of, you know, what these different, you know, modifying the loss function, how that affects our estimates that we would use, okay? So I've made a, some simple 2-dimensional data, okay? All right, so I have x1 is the values 1 through 4, and x2 is the values 1 through 4, but we've repeated them, you know, 4 times each, or 4, and I get basically a grid here. And here I'm not going to bother centering and scaling them because they're already on the same scale, okay? So technically their mean is not 0 and their standard deviation is not 1, but they, you know, x1 and x2 are both on the same scale. So I'm not going to bother trying to like recenter and rescale these things because they're already on the same scale. But yeah, in general, if you have an X matrix, you would center and scale them, okay? Just so that everything's kind of would have the same standard deviation and the same mean. These two already have the same mean and the same standard deviation. It just not happens to be 0 and not happens to be 1. Okay, so the true values are going to be the true relationship between x1, x2, and the outcome variable is that we do 1.5 times x1 plus 0.5 times x2. Okay, but then I add random noise. Okay, so I just do R norm and I add some random noise to this, and this is going to be our observed values of t. Okay, and so if I fit an ordinary least squares model to this data, okay, I'm going to say, so notice in our true relationship, there's no intercept, and I'm going to pretend I know that, and we're going to not fit an intercept here. I'm going to say, all right, let's predict the true value t using our x1 and x2 inputs, okay? You know, I forgot to give you a quiz question answer. All right, first quiz question. First quiz question is the letter C as in cat. C as in cat for the first quiz question. First quiz question, C as in cat. All right, so we are going to use ordinary least squares. Ordinary least squares says the best coefficients will be 1.4588, 0.453, okay? So it's kind of close to the true coefficients. True coefficients are 1.5 and 0.5, and ordinary least squares says you should use 1.458 and 0.453. Okay. Here's just to kind of reiterate the fact that all we're doing when we do least squares regression is that we are trying to optimize the least squares loss, okay? So the OLS loss is t minus xw transpose t minus xw, right? This is the sum of squares error. And so, so I've written a function that takes the observed data, your coefficient w1 and your coefficient w2, and it calculates t minus x times w times t minus x times w, right? T minus xw transpose times t minus xw, right? So w are your w coefficients, and x is the observed data for the x, and t is the column, observed column t, right? And then in order to use this with R's optimization function, so R already has a built-in optimization function that will find the values that minimize whatever function you provide. We're going to use this. But in order to use that, the optim function is always take everything as a function of par, okay? So what I'm going to do is I'm going to take par. I just create a wrapper function so that I can use this with the optimization function. So so here we have it, and we are going to, when we run optim, it says the values of W1 and W2 that minimize this least squares function that we wrote up here is going to be 1.45883 and 0.4533399, okay? Which is pretty much what LM has found, okay? So this is, we found these values by doing LM, and it's almost exactly the same. It's off by ever so slightly when I use optim. So we're saying optim, please minimize this, you know, t minus xw transpose t minus xw value. Please minimize it, and it came to these things. And the reason why it's different is because optim is iterative, and it's going to stop when the improvement is less than a certain epsilon. So it stops at something very close. But you know, this is pretty much it. All right. So and then I create contour plots. All right. And so this is a contour plot showing what our least squares loss function looks like, or what our squared loss function looks like for different values of W1 and W2, okay? So here it says the best W1 and W2 is right here at this red dot, okay? Which is has the coordinates 1.458 and 0.453, okay? So so this is gonna be the coordinate, you know, 1.458, 0.453. These are the values of W1 and W2 that minimize the loss function. So this is where we are here. All right, and so now what I'm doing is I'm going to modify the loss function, okay? I'm gonna create a new function called L1 loss. L1 loss is done, right, is this value is L plus lambda times our L1 norm, okay? So the L1 loss is we're gonna calculate the ordinary least squares loss, okay, plus lambda times the sum of the absolute values of W1 and W2. So we're going to take the absolute values of W1 and W2. We're going to sum those up, multiply that by lambda, and add that to the OLS loss. So this is the new loss function, okay? And we're going to try to minimize this new loss function. And in order to make it work with the optim function, I have to make it a function of par. So I basically do this, but this is what we have here. All right. Is this okay? So all I've done is I've written a new loss function, and the new loss function incorporates the OLS loss plus the L1 norm, which is lambda times the sum of the absolute values of our W vector. Okay, and so here first is the coefficients that minimize the regular old loss function. Okay, but now I have the L1 loss, and I have lambda equal to 10. Okay, we've got lambda equal to 10, and we're going to minimize this function. Okay, we want to find the values of W1 and W2 that minimize our modified loss function. Okay, so it says when W1 and W2 are equal to this, this is going to give us the smallest L1 loss. Okay, and if lambda is equal to 50, then these are the values that will minimize the L1 loss. Any other values that I pick will end up with a bigger L1 loss. How do you determine the value of lambda? The value of lambda is up to you, okay? And so here I'm showing different values. I have got lambda equal to 10, lambda equal to 50, lambda equal to 100. I'm going to keep increasing lambda. And you will see the effect of increasing lambda, okay? So you get to choose what lambda to use. And so these slides are here to illustrate what changing lambda does, okay? So that when it comes to making decisions, at least you'll have an idea of what it means to pick a different lambda, okay? Would it depend on the order of magnitude of the OLS loss? Yeah, yes. So depending on your original data, the observed data, and what your OLS loss is, picking different lambdas will have different effects. Yeah. So you can't just look at a data set and say, lambda's got to be 3 here, or lambda's definitely 37. Okay. But you can say, well, let's see what happens when lambda is this number, and maybe in this case it makes sense to increase lambda. Maybe in this case it makes sense to reduce the lambda. Okay. So I'm going to just show you the effect of increasing the lambda. All right, and so what we see here is that when lambda is small, okay, so when lambda is 0, basically the L prime, the regularized loss, is the OLS loss, right? Because this, if lambda is 0, then this term doesn't count at all. So the regularized loss is equal to the OLS loss. But as I increase lambda, then we're going to put more and more weight on that penalty factor for the complexity. So as lambda is equal to 10, we're going to say, well, we got to shrink down our coefficients, okay? When lambda is 50, we have to shrink down our coefficients more. Lambda equals 100, we shrink our coefficients even more. So the coefficient for x1 starts off at 1.458, but it goes down to 1.436, 1.345, 1.2231. Over here, it starts off at 0.453, it goes down to 0.430, 0.3397, 0.2259. So as we increase lambda, the coefficients for W1 and W2 start to come down. And as I increase lambda even further, they come down even more, okay? At lambda equal to 300, this coefficient is practically 0. And lambda equal to 500, both coefficients are 0, okay? At lambda equal to 500, we're saying the OLS loss, I don't care what they are. We don't want to incur any more penalty here, right? Increasing W really messes up the OLS loss, so it's not worth it. So we end up picking coefficients that are 0 here. So here's what the loss function contours will look like, okay? So right here, this is the contours of the loss function when lambda is equal to 10, okay? This red dot indicates the coefficients that minimize the ordinary least squares loss. The blue dot represents the coefficients that minimize the regularized loss when lambda is equal to 10. And what I'm going to show is I'm going to keep increasing the lambda, and you will see how the contours change and how the that coordinate of what's the best W1 and W2 terms will also change. Okay, so here it is with lambda equals to 10. At lambda equals to 30, we can see that it says, okay, we should pick a smaller W1 and W2. At lambda equals 50, W1 and W2 get even smaller. At lambda equals to 100, our W1 and W2 get smaller. And lambda 150, they both get smaller. And here's lambda 180. And at lambda equals 200, W1 is around 1, and W2 is basically 0, okay? And so I cannot reduce W2 anymore to get a smaller complexity, right? So to reduce my complexity factor, I can't reduce W2 anymore. If I go negative, it's actually going to increase the complexity. So W2 is not going to go anywhere. But W1 can keep going down. So as I increase lambda even more, it keeps going down until lambda is like around 500, and both coefficients have been reduced to 0. Okay, so let me just kind of go back. So when lambda is 10, W1 and W2 are pretty close to the ordinary least squares values. And as I increase lambda, we see the blue dot moving closer to the axis and down into 0, 0. Look at what happened to the contours also. Look at these contours. They're kind of crazy looking. So what's going on here, right? So if you think about it, what we're saying is that, let's add in, we're adding in the absolute values, okay? And basically, when you have the absolute value function, lines along here, will have equal values. So like, let's say W1 and W2, we know add up to 10. When if W1 is 0, W2 is 10. If W1 is 10, W2 is 0. And basically everything along that diagonal line, like W1 and W2 equal to 5, or W1 equals 6 and W2 equals 4, everything along those lines will have the equivalent value as far as the sum goes. But back here where lambda is quite small, we're not adding in that absolute value term quite as much. So the contours are guided. Remember, the contours are a combination of the OLS, which are ellipses, and the absolute value thing. So here we're giving more weight to the ellipses, and as we go here, now we're starting to add more weight to the absolute value thing, which is basically diamonds, and you get this effect here. All right, so this is a little bit of a summary here. As the lambdas increase, the contour lines begin to have sharp corners and straightish edges. And what we saw is that the parameter values traveled diagonally until it hit the x-axis and then was pulled towards 0. Let's explore this, but for ridge regression. So ridge regression, here's our loss function. The loss function is the OLS loss plus lambda times the sum of the w's squared. So we take the w's, a vector of w's, we square them, and we sum them up. And we add that to the OLS loss. And we want to minimize this function. We want to minimize the L2 loss. Okay. And so we start off at 1.45 and 0.453. And as we increase lambda, look what happens. Okay, x1, the W1 term, goes from 1.45 down to 0.249, down to 0.922, down to 0.74. But look what happens to when lambda is 10, 50, and 100. For x2, it actually starts at 0.453, goes up to 0.579, up to 0.635, and then starts to come back down to 0.573. So the W2 actually starts off down here and starts to go up and then back down. And as we further increase lambdas to 180, 300, 500, now at this point, both X1 and X2 both go down, okay? And so let me just show you what happens here. So red, again, is the OLS loss. If the lambda factor is 0, then the regularized loss is equivalent to the OLS loss. But as I increase lambda, then we're giving more weight to that complexity term, which is the sum of squared coefficients. So here's lambda 1, here's lambda 5, lambda 10, lambda 20, 30, 40, 50, 60, 70, 100. I don't know if Zoom is able to keep up with my slide changing, okay? But let me just, okay, so notice, follow the blue dot here. As I increase this, the blue dot is attracted to kind of this line here, this line W1 equals W2. So it gets kind of attracted to that, and then once it gets close to this line, it's going to start moving towards the origin here. Okay. All right, so what we saw is that as the lambdas increased, the contour lines looked less elliptical, more circular. And what we saw was that the optimal choice of parameters would actually move closer to this line W1 equals W2, and then when it got close, it got pulled towards 0. Okay, so why is it having this effect? Okay, so if you think about the L1 norm and the L2 norm, what happens is that the L2 norm will penalize larger values of W than the L1 norm. So the L1 norm, the LASSO, penalizes large values equally as small values. Whereas the squared values, okay, are penalized when they're larger. So if you think of, let's say you have two coefficients. One is, you've got two coefficients, 2 and 11. And we can say, let's reduce. We're going to reduce some of the coefficients, okay? So either we can push 11 down to 10, or we can push 2 down to 1, or some combination of, okay? So with the squared loss, okay, if I do the squared loss, or the squared coefficients as my measure of complexity, okay, 11 squared is 121. And if I push 11 down to 10, my complexity would go from 121 down to 100. I would gain, my complexity goes down by 21 points. Okay. On the other hand, if I take my take 2 and I push it down to 1, my complexity goes from 2 squared, which is 4, down to 1 squared, which is 1, and so my complexity only drops by 3 points. Okay. On the other hand, for the absolute values, if I push 11 down to 10, I gain 1 point. If I push 2 down to 1, I gain 1 point, okay? So as far as the absolute values go, pushing 11 down to 10 or 2 down to 1 has an equal impact. Doesn't really matter. So I might split the difference and push 11 down to 10.5 and 2 down to 1.5. Whereas as far as the squared values go, pushing 11 down to 10 reduces it by 21 points, from 121 down to 100, and pushing 2 down to 1 only reduces it 3 points. So I would definitely prefer to shrink the large coefficients first. So that's what we have going on here. When you have a large coefficient, it's going to push that one down first, maybe even at the expense of the smaller coefficient. Whereas with the L1, what we see is that it's going to kind of push both of them down equally until one can't be pushed down anymore, and then it pushes the other one. Okay, so here it travels diagonally because it's pushing both coefficients down equally. Let me show you this. Okay, so this, what this represents, the black dots that are hard to see here, what I've done is I've simulated my data again, okay? So way back here when I created my data is I picked random noise, 16 values from our norm, and I added that to the true t values to get my, my observed data, okay? I picked some random noise, which means that if I did this again, my random noise would be different and I would get different coefficients, okay? And that's what these slides represent. So this represents, this cloud of black points represents, you know, running the simulation again and just getting a different set of coefficients, okay? And what happens is if I ran it with different values of lambda, my different coefficients might have this kind of variance. And so what it ends up doing is it pushes the entire cloud kind of diagonally until it crashes into one of the axes, and then the entire cloud gets pushed all the way down to here. Now you can't really see it, but there's a blue dot here representing kind of all of the points got reduced to 0. Okay. On the other hand, this is what happens when you use ridge regression, the L2 penalties. The entire cloud of points actually shrinks, okay? Okay, and that the black dots represent all of the different estimates you might get for W1 and W2 for the different noise that we have. And here it is when we have lambda equals to 10. As lambda gets bigger, okay, the different values of W1 and W2 will are concentrated in this small, tight little cloud of points here, okay? And this cloud of points, the fact that it's small here represents that there's less variance as far as your coefficients W1 and W2 go. So the values of W1 and W2 will not vary as much when you have a larger lambda going for ridge regression, okay? Similarly here, when you have a larger lambda, your values don't vary as much because sometimes you're going to just get a whole bunch of zeros. And so these are ways that to reduce the amount of variance or variability in your coefficient estimates, right? So that's an undesirable trait that your coefficient estimates would vary a lot based on the random values you've observed. And so this is one way to kind of reduce that variance in the coefficient estimates that you get. Okay, and here's just a little summary page about that. Okay, second quiz question answer for today. Second quiz question answer is A as an apple. A as an apple for the second quiz question. So we'll end there for today. Have a good weekend. Stay safe and healthy out there, and we'll see you guys on Monday. All right. Let me stop my recording.